our speaker would be, the program would be at 10:30, so don't worry if they snugger in. It's my pleasure to introduce Professor Richard Wolfson, who is the, as most of you probably know, the Benjamin Whistler Professor of Physics at Radioactive College. Professor Wolfson started his education, his college education at MIT and Swarthmore, and then went into environmental studies, the master's at the University of Michigan, and from there he decided to do his doctorate at Dartmouth College. So that is his general background. He has written 5 different texts on various subjects, including university-level physics for students. He has written the climate change books. He's written on the nuclear choices that we have, and so it's quite a wide area of his expertise. He also, most recently, taught 2 new courses at Monterey, the International Institute, the various International Institute at Monterey, and I have to check my titles here. It's Power, Plutonium, and Proliferation, and then the second course was Climate Change, Assessing the Risk. So again, you see the extent of his expertise. We are very pleased to have him today, and I think you probably all read that Inkling notice, which explains basically what his topics for global warming are. And in addition, I would like to say that if anyone's interested, these are the great courses. They're wonderful courses on DVD, and this one was Physics in Your Life, which is blind, but he has done 5 courses for the great courses, and they're all very interesting. And if anyone's interested in looking at this, there's a list of his topics on the back. It's also very much easy for a layman such as myself, who does not have a science background, and English and library majors. And so it was a pleasure to watch this and listen to them. With no more, I'd like to welcome Dr. Wolfson.
Thank you, Lenore. So my goal is to give you a quick overview of the latest, and I really mean the latest, on what's happening with global warming, update 2016. I give this talk fairly regularly, but each time I give it, it's different because things are changing and our understandings of climate change have changed significantly. So I'm going to take you through a little bit of a process looking at climate change as we understand it today in 2016. If you have questions, especially short ones, what did that graph really say? What does this mean? Please ask them during the talk. And if you have longer questions that you want to debate something or whatever, we'll talk about them at the end. So I'm going to give you a little bit of science, a little bit of policy, and a lot of graphs that give us a sense of what we understand about global warming. First of all, the news. When I first started teaching about global warming and talking about it publicly, I was hard-pressed to find news items that related to it. Now it's trivial. A bunch of very recent news here about the wildfire near Canada. This morning, or yesterday's Times, global warming cited as wildfires increase in the fragile boreal forest. Let's see, up here, February broke the global temperature records by a shocking amount. February was the warmest February on record by far. Then March came along and it was the hottest March on record. April's gone down a little bit, it's the second warmest. For reasons we think we understand. Some islands disappeared. 7 May, just a few days ago, Australia's coral reefs. David is just back from Australia. He can probably tell us more about that. Bill McKibben got arrested last fall in a gas pump protest. A lot of things going on here. It's not all bad news. Anyone see 2 pieces of good news?
175 nations signed historic.
Okay, 175 nations signed the historic Paris climate deal on Earth Day, and here's John Kerry with his granddaughter signing that for the United States. There's another one. Peabody Energy went bankrupt, the world's largest coal company. Sign we're moving away from coal, which we need to do. Probably the worst one on here, though, is in the lower right. The concept of global warming was created by and for the Chinese in order to make U.S. manufacturing non-competitive. Your presidential candidate speaking. So I want to raise three big questions and attempt to answer each of them. First of all, is the climate changing? I want to give you evidence for that, and it's not just the evidence you hear most about: melting ice, rising temperatures. There's a lot of other things that provide evidence for climate change. So what is the evidence and how do we know? What's the cause? We're the cause. We know that by now for sure, but how do we know that we're the cause? And finally, a quick look at what the future might bring in terms of climate. So that's where we're going, and we will start with this question: is climate changing? And look at some evidence for it. I'm going to be citing the Intergovernmental Panel on Climate Change a lot, the IPCC, and I want to say a little bit about what the IPCC is. It issues these assessment reports about every 6 years. So the most recent one was released in 2013, 2014. That was the AR5 assessment report number 5. They try to summarize the state of the world's understanding of climate. They look at thousands and thousands of papers in the scientific literature, and they put together this synopsis of what the state of our knowledge is. There are 3 working groups. They publish 3 big, thick volumes, and if I hadn't walked here to keep my carbon footprint down, I would have brought you my great, big, thick, just volume 1 of the IPCC. So the first one is about science, the physical science basis. That's the part I deal most with. Impacts, adaptation, and vulnerability. The course that Lenore mentioned that I taught at Monterey a couple years ago used that one. What are the impacts and how do we adapt to them? And finally, mitigation of climate change. What can we do to decrease the happening of climate change, to reduce its effects? And finally, there's a synthesis report that puts this all together. Now, this is far more than you want to read. It's thousands and thousands and thousands of pages, some of them pretty detailed scientifically. However, there are summaries, and I strongly recommend anyone seriously interested in climate change look at the summaries. There's a summary for policymakers. It's about 20 pages long, and it tells heads of state and government officials and disaster planners and people like that what they need to know to understand climate change. And then these are approved by 195 member governments. These are not some left-wing conspiracy. The government of Saudi Arabia, which has a great interest in pumping oil out of the ground, has to sign off on these documents. There are 678 authors from more than 78 countries and almost 2,000 expert reviewers also. There are also technical summaries, which about 80 pages long, and the technical summary is itself sort of a great tutorial introduction to climate change. And you can get all these documents at ipcc.ch, or you can buy them at great expense from Cambridge University Press in hard copy. I recommend reading them online. So let's move to my first question: is the climate changing? Here's a look at the global temperature from the year 1000 to 2015. The temperatures from the year 1000 to about the mid-1800s are based not on temperature records, because we didn't have thermometers way back then. They're based on things like tree rings, radioactive isotopes, coral reefs, a host of other proxies that we can use to understand what the global temperature was at those times. And then the most recent part of it is based on the actual temperature record rising up here to 2015. We had a real spike just in the last couple of years here. This graph is a very famous one. Anyone know the name of it? It's called the hockey stick. It was put together by Michael Mann, who was at that time at the University of Massachusetts, a climatologist, and Mike did this work on the proxies, figuring out how you could reconstruct climate going back 1,000 years, produced this graph, which became an iconic part of the third assessment report of the IPCC, and you can see why it's called the hockey stick. It goes down gradually and then ticks up. Now, it's looking less and less like a hockey stick as time goes on, because that uptick, the end of the stick, is getting longer and longer, and pretty soon it's going to be longer than the handle. But that's how things are. Now, Michael Mann took a lot of grief for that. By the way, he has hanging on his office a hockey stick from the championship, I think, 20-something hockey team from Middlebury College, because he was one of our big environmental speakers here a few years back. He took a lot of grief for this. A lot of climate skeptics, this makes no sense. So a bunch of other climate scientists jumped in, and we now have a whole hockey team that have reconstructed temperatures going back now 2,000 years, and the picture is pretty much the same. Some variation. There's a so-called medieval warm period, and then cooling gradually, but then this uptick. And the takeaway message from this is we're seeing climate change at both a rate and a magnitude that's certainly unprecedented in at least the last 1,000 to 2,000 years. So let's take a look at the more recent temperature record, the temperature record for the Anthropocene. What's the Anthropocene?
Human life.
Anthropocene. What's Anthropocene mean? What is the Anthropocene? You know, the Paleocene, the Holocene, the Oligocene, all these things my geologist colleagues know about. What's the Anthropocene? It's the period in which humankind has had a significant influence on the natural order. So on the planetary systems, the systems of Earth. And there's a lot of debate on what should define the Anthropocene, because geologists require some kind of definitive, permanent marker in the geological record to define a new era. So they're debating, and two of the suggested times are 1945 with the first nuclear weapons tests, because they left a layer of radioactive stuff which is going to be there for tens of thousands of years. So that's a marker for when that started. Others say maybe it's the age when plastics became distributed all around the Earth. Others say it's way back in the 15 or 1600s when we started burning coal in large amounts. You can debate when the Anthropocene started, but we're certainly in the Anthropocene now. And I want to just look a minute at the Anthropocene temperatures. This is a record from the University of East Anglia Climatic Research Unit. I updated it just a few days ago. You can go to the University of East Anglia. They have one of the best temperature records on the planet. There are 4 or 5 different independent groups that keep records of temperatures. These are based on thermometers spread all around the world. A lot of statistics goes into this to make a global average. The zero is meaningless as far as temperature changes are concerned. It's basically an average temperature from about 1960 to 1990, but that doesn't matter. All that matters is the variations. So in the early part of this record, from 1850 to the early 1900s, the temperatures were below about that late mid 20th century average. Then they fluctuated around. They actually dropped a little bit after World War II, and we think we understand why that was. And then around 1970s, 1980s, there started this very steep rise. It slowed a little bit in the early 2000s. That was the famous hiatus that the climate skeptics latched onto and said global warming has stopped. But in the last few years, it's really come back with a vengeance. And that's just the last couple of years on there, really huge spike. So that's what the Anthropocene temperatures look like. If you go to that same record that I took the data to make that graph, and you ask, what are the 20 hottest years on record? Well, there they are. The last 2 years, 2010, 2013, the red ones are the current decade, the orange ones are the decade before, and 1998 was right up there. Why? You know why 1998 was up there? It was a big El Nino year. And this is a big El Nino year, and the El Nino, the phenomenon of upwelling of water in the Pacific, affects global climate and does tend to give us warmer years. So part of the reason it's been really warm the last couple of years is because of the El Nino. Does that mean it's natural? No. The occurrences of El Ninos are less and less natural these days, and that's on top of the human-caused warming. And then there's the next 10, still a few in the 1990s. You'll notice we have 1990 on here, but we don't have anything in the early 90s. There's an interesting reason for that I'll get into later. And already, with January, February, March, and April determined, it's almost certain that 2016 will be the warmest year on record, because 3 of the 4 months were the warmest on record, and the next one was second. So next time I show this, 2016 will be up here, 1990 will have dropped off. So you saw this picture. I was showing this movie for a while before things started up, so I won't bother to show it again, but this looks at the regional distribution of those temperature changes all the way. Well, let me just show it quickly once. We'll run through it. So we're going to go up in 5-year, these are 5-year averages taking us up to 2015. There's a scale here. Hotter is the redder, yellower colors. You can see different parts of the world are warming at different rates at different times. Some places cool, the places that get bluer, cool. And here we go, we're into the 20th century, late 20th century, and suddenly things really start taking off. And there we go. And we end at 2015 with a much warmer world than we started with. So the climate is really changing. Now, again, it isn't just about temperature. It's about lots of other things. For example, we hear about sea level rise. Sea level is rising. It's rising at about, in the last decade or so, it's been rising about 1/8 of an inch a year. That doesn't sound like a lot, 3 millimeters. That is faster than the average rate through the 20th century, which was closer to 2 millimeters a year, more like 1/10 or 1/12 of an inch. So it's rising, and you can just barely see on this graph, which goes from 1980 to about 2010, you can see that graph is beginning to slope more steeply upward. It's not terribly obvious, but there it is. And what we're looking at here are 3 different graphs of 3 different data sets that attempt to measure sea level rise. We can measure sea level from above with satellites. The most common way to measure is with these devices, which are tide gauges, which are deployed around the world and measure sea level. And just to give you a sense of what sea level rise means, here's a look at what Florida would look like, the red are areas that would be inundated, if we had 3 meters, about 10 feet of sea level rise. We're nowhere near that. We're not going to see that in this century. If you've got real estate in coastal Florida, you have to worry this century, but it's not going to be deep underwater like that map shows. But there are other things. For example, we'd really like to know where all that extra energy from the sun that's being blocked by the greenhouse gases that we're putting in the atmosphere, where's that going? Well, it's going, most of it, into the ocean. If it weren't doing that, the planetary surface would have warmed up a lot faster. So this is a graph that goes back from about the mid-20th century up to 2015. And it shows several averages, 3 months averages, yearly averages, 5-year averages of the amount of energy that's been stored, in this case, in the first 700 meters, that's about 2,000 feet of the ocean. So this is not just a measure of the temperature of the ocean, it's a measure of the actual energy that's being stored in the ocean, and that's going up. And the people who thought there was a hiatus in global warming in the early 2000s, well, this thing continued to go up. Surface temperatures, they continue to go up too, but they at a more slow rate. But the important thing is the energy that was being stored in the Earth system, mostly in the oceans, just continued to rise and is continuing to rise and going up a little more steeply. So ocean heat content is not something you hear about, but that's one of the most profound measures of climate change, because it's actually measuring the energy, the extra energy that's being dumped into the Earth system. The shrinking Arctic, we have had good satellite measurements since 1979 of the extent of ice in the Arctic Ocean, and every year, usually sometime in September, once in a while in late August, there comes a time at the end of the Arctic summer when the sea ice is at an absolute minimum, the lowest it's going to be, and then it's going to start to build up again. And so we measure that minimum, and here's what it's been looking like since 1980. It's been gradually declining until about 2000, and then a much steeper decline. And I remember when 2007 happened, and they said, that's a real outlier. It's not going to be anywhere near that low again. Well, the next year was pretty low, too. Then it kind of bounced back up to this rather rapidly steepening curve. Then it fell again 2012, a real minimum. Came back up and came back down again in 2015. And of course, we've all seen this iconic image of the poor polar bear sitting on the what's left of the ice floe. But that's a really substantial drop. These are the millions of square kilometers of ocean that's covered, and it's gone from about 8 to as low as close to 3. So we've lost, on average, something like about half the ice cover in the Arctic Ocean just in a period of 3.5 decades. What's it look like if you don't like graphs? Here's a picture of the sea ice minimum, that September day in 1980, a reconstruction from satellite images, and here's the same thing in 2012, which happened on September, I forget the date, it happened on September 11th this year, it happened on September 17th the year before, I forget the date, some day in September. And this yellow curve is sort of the average over the last few decades. It's a very tiny amount of ice compared to what there normally is there. So another thing that's happening is the cryosphere, the part of the Earth that's covered with ice and snow, is undergoing profound changes. Another example of that are the glaciers. And these glaciers are not just way up in the Arctic. These glaciers are, some of them, at the equator, Mount Kilimanjaro. The glaciers in Kilimanjaro are shrinking dramatically. Here's a glacier in Glacial National Park, the Shepherd Glacier, taken early in the 20th century, taken early in the 21st century, major change. The Tift Glacier in Switzerland, here's the glacier, there's a little bit of it left, now there's just a lake. McCartney Glacier in Alaska, here it was in 1909, here it is about 100 years later, gone. The Muir and Riggs Glaciers, both in Alaska, that one and that one, they were a big sea of ice in the 1940s. Now there's still a glacier there, but the rest of it is just open ocean. So we're seeing changes in the ice of the world, and those changes are important because ice reflects sunlight, and if you get rid of ice, you absorb more sunlight and you enhance global warming all over again, which is why the Arctic is warming faster than anywhere else. The Antarctic is also undergoing climate change. A lot of people, skeptics particularly, have picked on the Antarctic. Well, Antarctica isn't melting like the Arctic, and it isn't. And there's a big difference between the Arctic and the Antarctic. What's the great, big, huge difference? Land. The Antarctic is a continent with land. The Arctic is an ocean. And that makes a huge difference in how they respond climatically, because the Arctic has only a few meters thick of ice on it. The Antarctic has miles of ice on it. The Antarctic ice is not going to melt for thousands of years, even if we try to melt it. So it's very different. But there are these collapsing ice sheets, and this is a famous event, the Larsen B ice sheet, which collapsed in 2002, lost a region of ice about the size of Rhode Island. There it is in January, there it is in February. You can see it, you can see it beginning to break up. And there it is in March. It's all broken up, and a little bit of new ice has formed on the surface, but that's not an ice shelf. That's got just a little thin layer of ice with some snow on it. That is not going to reform. We lost an amount of ice, roughly the area of Rhode Island in that event. And we now think that the retreat, the collapse of these West Antarctic ice sheets is probably irreversible. It's probably going to continue, and there's nothing we can do about it, at least for hundreds to thousands of years. Many other indicators of recent climate change. I mentioned some aspects of ice and snow. There's been a 40% decrease in the Arctic ice thickness, something we didn't know about for a long time because the data for this were taken by nuclear submarines going under the Arctic during the Cold War. And when that data was finally released, we were able to get measurements from their pinging their sonars off the ice pack from underneath of how thick the ice pack was. It's decreased by about 40%. There's a decrease in Arctic ice extent, as you've seen, since 1950. There's been a 10% decrease in global snow cover in the winters. There's been a widespread retreat, as I showed you in those pictures, of non-polar glaciers. There are changes in weather patterns. The El Nino has become more frequent, more persistent, and more intense. That's why I said the El Nino that's going on right now is not an entirely natural phenomenon and is contributing to the excessively warm years we're having now. There are more intense precipitation events. This is very clearly established. When it rains harder for shorter times. There's also more precipitation because a warmer atmosphere can evaporate more water and can hold more water, but when the water falls, it falls in more intense events, and that has implications for agriculture, for erosion, for things like that. It's a little harder to grow crops when the rain doesn't come gently and frequently, but comes infrequently and intensely. And tropical storm intensity is increasing somewhat in some oceans, particularly in the North Atlantic. I know that people who are concerned about global warming, one of the favorite images is of, Hurricane Sandy, Hurricane Irene, all these extreme weather events. Some extreme weather events are, in fact, tieable to climate change, but that is one of the weaker links we have. Most of the other impacts I'm telling you about are much more solidly established, so I'm not going to spend a lot of time on storm intensity. Then there are biological indicators. The growing season is increasing at the rate of 1 to 4 days every decade. I put my tomatoes in early May these days. I used to put them in on commencement weekend, which is Memorial Day weekend, because I can do that now with this increase in the growing season. Plant and animal ranges are shifting poleward. Coral reefs are bleaching. There's a lot of news lately out of Australia on that. And I want to look in a little bit more detail at this issue of some of these biological indicators. What does phenology mean? It's not that thing they used to do with your head. Remember that? You looked at your head and drew pictures of who you were. I forget what that's called. What's that called?
That's phrenology.
Okay, so what is phenology? It's a great time for phenology out there now, because phenology is sort of the study of the periodic life cycle events. And if there's ever a time to see them, it's spring. So you look at things like when birds start making nests, when blossoms come out, when bud burst occurs, the kinds of things you see happening in spring. And you study when that occurs. And one of the most famous studies in climate change is this meta-study of hundreds and hundreds of studies that were done by individual species. And scientists combed through those studies, and they found that in the northern hemisphere, species are in general, not everybody, but most species are moving northward about 6 kilometers, that's about 4 miles, every decade. Now, if you're a species that can get up and move, that's great. If you're a tree, it's a little harder. You've got to drop your seeds, hope they grow, maybe you can't. And then if you're an animal species that can move, but you've got to eat the tree that can't move, well, you're out of luck. Mountain species are moving upward at 6 meters per decade. I mean, if these trends continue, Quebec is already the biggest producer of maple syrup in the world. Vermont will be out of it because maple trees are going to move northward. Probably. There's a lot of subtleties in this biological stuff, so it isn't a perfect representation of what's happening, but it's happening. And mountain species tend to be moving upward at about 6 meters. That's about 20 feet per decade. And so if you're a mountain species and you move up and up and up and suddenly you come to the top of the mountain, there's nowhere to move, you're gone. You're extinct, at least on that mountain. And spring events are occurring typically 2 to 3 days earlier per decade. Each decade they advance by 2 to 3 days, including nesting, breeding, bud burst, flowering, end of migration, things like that. Okay, so I've given you a number of indicators that the climate is in fact changing, and changing fairly dramatically. I've talked a lot about temperature. I want to give you just a brief sense of how we know and understand and take Earth's temperature. So how do we take the temperature of the planet? We have a number of data sets. We have data sets like sea surface temperatures that are measured by ships that measure the temperature of the water routinely as they plow through the world's oceans. They measure the air temperatures above the ocean, marine air temperatures. We have weather stations all over the world that measure surface air temperatures. And we have balloons that we send up into the lower troposphere, the lower atmosphere. And we also have satellite imagers that look down from above, and they can measure the temperature in the lower atmosphere. And I've just given you here a graph from 1975 to 2010 of all kinds of these, some over the land, some over the surface, some over the oceans, and they all basically are telling us the same thing. Namely, that the temperature is going up by all these measures. They all agree. Now, we have to be careful. I mean, we have thousands of thermometers. A thermometer on the equator, measures 98 degrees Fahrenheit. A thermometer in the Arctic measures minus 10 degrees Fahrenheit. How do we get them all together? Well, a lot of statistics goes into that. That's one of the reasons we don't talk about what is the temperature of the Earth, but what's the temperature change. Because the temperature change in Vermont might be comparable to the temperature change in Florida, even though the absolute temperatures aren't the same. So we have to do some work on this. We have to do some corrections. For example, instruments change. The kind of thermometers we use change. Sometimes the location, there's a standard height for thermometers. It's about this high if you build a weather station. But in some parts of the world, they were lower or higher, and we have to correct for that. Sampling techniques. Sea surface temperatures are a brilliant example. In the old days, they would throw a bucket overboard, haul the bucket up, stick a thermometer in it on the deck of the ship, and measure it. And some of the buckets were made with wood, which is a fairly good insulator, and some of the buckets were made of canvas. And if you're ever a Boy Scout, when I went to Boy Scout camp, we had this great big canvas bag called a Lister bag, and we filled it with water and hung it from a tree, and the water evaporated through the pores in the canvas and kept it cool. Well, if you bring up the water in a canvas bucket, that effect occurs, and you get a lower temperature. So we have to correct for that. And then around World War II, we started taking the temperature at the intake of the engines of the ship before the water had gone through the engine. And that was a direct measure of the surface temperature of the sea. And so we had to correct for all that. One of the most important corrections, actually it's not that important, but in the eyes of skeptics it is this so-called urban heat island effect. And the idea is this. You built a weather station way back when, and two things were happening. First of all, the city wasn't nearly as big. Now cities, which generate a lot of energy for heating and transportation and have a lot of black surfaces that absorb sunlight, they tend to be warmer than their surroundings. Another effect that's more subtle is you build a weather station on the outskirts of the city, and then the city grows and surrounds the weather station, and the temperature goes up. And that's not global warming, but it looks like it. You measure the temperature over time in that city, and it looks like it's going up. Well, it is going up, but not because of global warming. So we correct for that. And Boston now looks like that. You're going to get a bigger, higher temperature in your thermometer. Some of the data sets that measure temperature correct for this, and others say it's so small, it's about 0.05 degrees, that we don't worry about it. And you can do that by looking at those temperature data sets and just excluding the big cities. So if you ever hear a skeptic say, well, this is all about the urban heat island effect, it isn't. You get the same temperature rise almost if you leave the cities out altogether. So I just want to mention that. But there are a lot of changes or corrections that have to be made to get these numbers that we say are the global temperature. Okay, so now I'm on to my second question. What's the cause of this climate change that's occurring? And here I'm going to give you a little bit of science. And I'm a physical scientist, so when I teach about climate change, it's a little different than if my biologist colleagues did it or even my geology colleagues. I want to get at the basic physical science, the basic physics behind this. So here's the big idea. The big idea is something called energy balance, and you all know about this. Any system that maintains a constant temperature, it sounds complicated and sciencey, it will maintain a constant temperature if the rate at which energy comes in is equal to the rate at which energy goes out. And you all know this because you all pay heating bills in the winter. You pay for firewood, you don't pay for your photovoltaic energy that runs your heat pump, but you have to provide energy to keep your house warm. You pay for oil, you pay for gas, you pay for whatever you're paying for. What's going on in your house is this. Your house is an imperfect heat container. It's got insulation in the walls, I hope. It's got good windows, I hope. But nevertheless, energy escapes through the walls of your house to the outside. And you have to replenish that energy. And if you manage to replenish it at the same rate at which it's leaking out, then your house stays at a constant temperature. And what your thermostat does, here's the thermostat in here, what the thermostat does to achieve that is to turn the heating system on and off as it needs to. If it gets too cold, it turns it on. It gets too hot, it turns it off again. And on average, the rate at which your heating system is supplying energy is equal to the rate at which energy goes out. And that's a basic principle of physics. If you want to maintain a constant temperature in a situation where you are losing energy to the outside, or gaining it in the summer, then you have to take energy out. If you're losing energy to the outside, so your surroundings, you have got to supply energy to replace the energy that's lost at the same rate. And that's the idea of energy balance. What if you're out of balance? Well, if you're out of balance, then the temperature is going to rise or fall until the balance is established. And here's a sort of science principle to keep in mind. And that occurs because the rate at which something loses energy depends on how different its temperature is from its surroundings. Why does it cost more to heat your house in February than it does in April? Because the outside temperature in April is warmer, and the loss of energy from inside your house is still at 68 degrees or whatever, both months. But the energy loss rate is much greater in February because of that bigger temperature difference between inside your house and outside. And so even if you didn't have a thermostat, if your thermostat failed, I hope this doesn't happen to you, but if it failed and left your heating system on, just running, your furnace running all the time, would your house heat up and 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 heat up until it burst into flames and exploded? No, it wouldn't. Because what would happen is it would heat up and heat up and heat up. And as it did so, the temperature inside would get greater and greater and greater. The outside is still cold. The rate at which energy would be lost would increase and increase. And eventually there would come a point, a temperature inside, at which the rate of energy loss would equal to the rate that your furnace is putting out heat, and then you'd be at a constant temperature. It'd probably be a high and uncomfortable temperature. Exactly what it was would be determined by how much heat your heating system puts out, and also by how good your insulation is. So let's look at a very simple example. Here's a greenhouse. This greenhouse is warmer than its cool surroundings. Why is it warmer? Because energy is coming in from the sun. I'm assuming this greenhouse doesn't have any heat source inside it, and it's losing energy, and when it's in balance, the energy coming in and the energy out are equal, and that establishes a temperature in here which is warmer than the outside. If it's too cool, the energy in is still the same. It's coming from the sun hasn't changed, but the energy out is less because the temperature difference from inside to out is lower, and so more is coming in than going out, and the temperature goes up. And if you're too hot in the greenhouse, meaning hotter than that balance, then the energy coming in is still the same because the sun hasn't changed, but now there's a bigger temperature difference. The energy out is going to increase, and it will go out and eventually bring the system back into balance. That's how a house or a greenhouse stays warm. Okay, you with me? Because now we're going to go to a planet. Okay, so here is Earth. Earth is just like the greenhouse, sort of. In comes energy from the sun. We can't do anything about that. The sun supplies that. The Earth heats up, and the Earth's way of getting rid of the energy from the sun, of being in balance, is to emit infrared radiation. Infrared is invisible light that you can't see. It's redder than red. The energy that the Earth emits is very much redder than red. It's sort of what you would feel if you held your hand near a hot stove burner that was on so low you couldn't see it glowing. You'd be feeling the infrared. And that's what the Earth does. And if you take my climate change course at Middlebury next fall, you would be asked in the first week to do this calculation in which you equate the incoming sunlight to the formula for the outgoing infrared, which depends on temperature. Remember, the hotter the temperature, the more stuff goes out. And you would get this interesting result that the temperature of the planet is 255 Kelvin. This number, where a Kelvin is, that's about minus 18 degrees Celsius, about 0 degrees F. Now, does that sound reasonable for the average temperature of our planet? Well, it sounds a little cool, right? Now, it's not totally unreasonable, you know, because it could have come out 500 degrees and the oceans would have boiled away. That's what happened on Venus. It could have come out minus 200 degrees and the oceans would be frozen solid. So it's not way out of line, but it does seem a little bit cool for the average temperature of the whole planet that's got Florida and Ecuador and Brazil and sub-Saharan Africa and warm places like that, as well as the Arctic and the Antarctic and then temperate places like us. So something else is going on. What's going on is the greenhouse effect. You've all heard of the greenhouse effect. I want to give you just a little bit of scientific sense of what the greenhouse is. So what happens is this. There are in the atmosphere gases. What's the atmosphere made of? Mostly? Nitrogen. And what's the second one? Oxygen. Okay. Those are transparent, basically, to visible sunlight. You can see the sun. You can see the stars. They're also transparent to that infrared that wants to get out. But there are other gases in the atmosphere, a lot of them. Most importantly, water vapor, and carbon dioxide. And they are opaque to infrared. Because of their molecular structure, they tend to absorb this infrared that the Earth is trying to get rid of. And they heat up as a result of that, and like any other hot thing, they give off more infrared, and they radiate energy out into space, and they also radiate energy back to the surface. And that makes the surface warmer than it would otherwise be. And before we human beings came along and started messing with the balance of gases in the atmosphere, that effect was about 33 degrees Celsius, about 60 degrees Fahrenheit. Remember, the Earth was coming out originally 0 degrees Fahrenheit. So the average temperature of the Earth is actually, or was actually, before human beings began messing with it, about 60 degrees Fahrenheit or 15 degrees Celsius, because of this so-called natural greenhouse effect. And it makes the Earth a much more hospitable place than it would be. It wouldn't be uninhabitable without the greenhouse effect, but it's a lot better. It's a lot nicer place to live. So we like the greenhouse effect, at least this natural greenhouse effect. And I always ask my students, what's the magnitude of the natural greenhouse effect? Give me a number. It's about 33 degrees Celsius, about 60 degrees Fahrenheit, warmer than it would have been because of that. So there's a couple ways to understand this greenhouse effect. I think every elementary school student, you people are retired teachers mostly, so you don't get a chance to go out and do this again unless you still go into the schools and volunteer. But your younger colleagues who are still teaching, every elementary school student in the world ought to understand that the greenhouse gases act like an insulating blanket. Because they know what happens when they put a blanket over them at night. They feel warmer because it's hard for the heat to escape from their body. And it's the same thing. Now, this is a sophisticated audience of people who want to understand things a little bit more detail. So here's a better way to understand it, or a more sophisticated, a little deeper way. The greenhouse gases up there in the atmosphere absorb this outgoing infrared that the Earth is trying to radiate to keep itself in balance, and they re-radiate some of it back to the surface. And the surface is therefore warmer than it would have been. So that's a sort of explanation for the greenhouse effect. Now, that was the natural greenhouse effect. But we human beings have been messing with that by putting more of the greenhouse gas, particularly which one? Carbon dioxide. We also put more water vapor in. We also put some other substances in, like methane and so on. But carbon dioxide is the biggie, and I'm going to mostly talk about that. And here are the contributions we think, the things that we humans have done to global temperature change, the overall global warming from about 1950 to 2010 was a little over half a degree. This is based on 2010. By 2015, it's significantly different than that, significantly higher. There's the observed warming. These little funny H-like things on the ends are the uncertainties, the scientific uncertainties. There's the effect of the greenhouse gases, carbon dioxide, methane, the chlorofluorocarbons, other things. Not quite so certain about them. We're very certain about the carbon dioxide, as I'll show you in a minute. But they alone would have warmed things more than it is now. But the other so-called forcings, the things that change the balance of energy in the climate, are actually negative. They actually exert a cooling. You know what the dominant thing there is? Exerting a cooling effect that we humans are doing? It's the so-called sulfate particles, the sulfate aerosols we're putting in the atmosphere. And you know where they come from? Coal burning, largely. So if we cleaned up our act and got coal to burn cleaner, that is, with less pollution, because that sulfur dioxide is killing 7,000 people in the United States every year also, we would actually make global warming worse. because we do have a little bit of a cooling effect. And of course, there are some skeptics who are like, well, there's no global warming because the coal, makes this stuff that cools us. Well, it does, but it doesn't cool us as much as the greenhouse gases warm us. You combine those two, you get basically the warming we have. There are some natural forcings, natural changes. One is internal variability in the climate system. Yes, the climate varies naturally. We don't understand it fully. We know the limits on it are pretty small, and natural forcings due largely to the sun, and sporadic changes in the sun and sporadic volcanic eruptions have a fairly negligible effect, at least in recent years, compared to the anthropogenic, the human effect. So let's talk about these greenhouse gas emissions and where they come from. Here's a look at where they come from or what kind of gases they are. Carbon dioxide is the vast majority of it from fossil fuel burning. That's why Fran is busy trying to divest of fossil fuels. That's why I walked here instead of driving my car. That's why we're trying to limit our consumption of fossil fuels. That's why some argue for the pipeline, and that's why some argue against the pipeline. There's also carbon dioxide from other effects. Deforestation, when we cut down a forest, that forest fire in Canada that just happened, is still going on, is dumping a lot of carbon dioxide in the atmosphere as the wood burns. So deforestation, decay of biomass, that's producing a significant chunk. Other is largely the production of cement. Makes carbon dioxide. Methane comes largely, but not entirely, from agriculture, also from leakage of natural gas, as those of you who are working against the pipeline know, and some other gases. So there's a lot of gases, but carbon dioxide is the biggie. By what kind of source? Well, energy supply is the biggest single contributor. That means generating electricity, basically. Transportation is a big part, industry is a big part, agriculture, forestry, buildings, wastewater, and so on. So a lot of things we humans do result in the production of greenhouse gases, which by and large go into the atmosphere. So let's look a little bit more at CO2. Here's sort of the historical record of CO2. We have very good measures of CO2. The best way to get those is to look at air bubbles trapped in ice cores taken from the Arctic and Antarctic and Greenland. But there are many other ways to get at it. There is a record. We are, as of February, at about 407 parts per million. Last time I taught climate change course a couple of falls ago was the first time it was over 400. It was just touching 400. Now it's obviously well over. Since the 1950s, we've been taking data at lots of places, but in particular, there's a beautiful observatory on the side of Mauna Loa in Hawaii, 10,000 feet up, on a piece of land, none of which is more than 150 years old, because this is an active volcano. And this station is high up, measuring very well mixed air from the relatively pollution-free Pacific Ocean. So it's getting a really good measure of the world global carbon dioxide. And this is wonderful data to play with. I have my students play with it. So this is a curve from about 1950 to now. And you see these wiggles, and those wiggles are not noise. You know what those wiggles are? They're the seasons. Because where's most of the land on the Earth? It's in the northern hemisphere. And so when the land plants come out of the northern hemisphere, what do plants take out of the air? Carbon dioxide when they do photosynthesis. So as spring comes on, the plants begin removing carbon dioxide from the atmosphere, and it goes down. And then when fall comes and they begin to lose their leaves and so on, then the carbon dioxide goes back up as they respire, but they don't photosynthesize. You might say, what about Australia? What about, way down in southern Africa? Well, yes, but they don't have as much land mass, and so the effect is dominated by the northern hemisphere. This is a really pretty curve to look at and think about. So when I said February we were at 407, that's probably not the global average for 2016. It's going to be lower than that because February is getting near the end of the winter when the plants have been respiring but not photosynthesizing for quite a while, and so the level is up a bit. So there's the historical record. There's what it is if you go back 1,000 years. It looks an awful like that hockey stick. But this is not temperature, but carbon dioxide. And just some examples of some of the things that are causing it. Now let me get to my most scientifically complicated slide, but it's just words. I want to convince you that we know that we human beings have caused this recent increase in CO2, because some of the most extreme climate skeptics are still saying, oh, CO2 is a natural thing in the atmosphere, and humans don't have anything to do with it. First of all, most of the CO2 is coming from fossil fuels. And these are things we buy and sell. They're commercial commodities. So we keep track of them. We even kept track of coal sales in London in 1600s. So we know how much we're buying and selling. We track their consumption, and that consumption and burning up of it, because that's how we consume them, is consistent with increases that we've seen in atmospheric CO2. Here's the more scientific one, which is fascinating. Tick, 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 tick. She's radioactive. This guy is too, but that's because he used to work in a nuclear power plant. You're all radioactive. And the reason you're radioactive is because there's a special kind of carbon that is formed in the atmosphere by cosmic rays from outer space hitting the upper atmosphere, and they make this radioactive carbon, which only lasts about 5,000 years. And plants do photosynthesis. And so they pull carbon dioxide out of the atmosphere, and some of that carbon dioxide has this radioactive carbon in it. And so the plants are radioactive, and when we eat the plants, or if we're not vegetarians, we eat the beef that ate the plant, and we all living things get radioactive. A little bit. Don't worry about it. It's there. When we die, we stop eating, and we stop taking up radioactive carbon dioxide, and the radioactive carbon dioxide decays away. And by measuring the amount of radioactive carbon dioxide, carbon, now in dead matter, you can determine how old it is. That's called radiocarbon dating, and you've all heard of it. Archaeologists use it. But for our purposes, the atmosphere, the new carbon that's going into the atmosphere doesn't have as much of this radioactive carbon as we would expect for stuff that is coming from currently living things. So it's a hint that the new atmospheric carbon has been out of contact with the atmosphere for a long time. It's carbon-14. So there's one piece of evidence, out of the atmosphere for a long time. There's another kind of carbon called carbon-13, which is also not very common, but it's not radioactive, perfectly stable. And the carbon-13 it'll occupy a little tiny fraction of the carbon. But plants who do photosynthesis, they like to work with the lighter molecule carbon-12. 12 means it has 12 protons and neutrons together. 13 means it's got an extra neutron, so it's a little heavier. So they don't like the heavy stuff quite as much. The chemistry doesn't work quite as fast. And so they preferentially take up carbon-12. The fact is there isn't as much carbon-13 in the new carbon that's going into the atmosphere, and that's a very strong suggestion that the carbon that's going into the atmosphere today is coming from plants, and it's coming from plants that have been out of contact with the atmosphere for a long time. Well, that's the fossil fuels. They've been buried for hundreds of millions of years, and they come from plants. That's very strong evidence that the carbon in the atmosphere comes from our burning fossil fuels. Here's one other piece of evidence. The oxygen content is decreasing. Gas. I can't breathe. Well, it's not decreasing that much. Don't worry about it. It's not going to suffocate us. But it is going down measurably, and it's going down enough that it is consistent with the missing oxygen combining with the carbon from the fossil fuels to make carbon dioxide. So evidence that the carbon dioxide in the atmosphere is coming from us, and it's going to be with us for a very long time. Now let's talk briefly about how carbon dioxide and temperature go together. So here is a complicated graph that shows in red the temperature deviation from some average over the last 160,000 years. And there's this interesting pattern. It was warm about 130,000 years ago for a little while, a few tens of thousands of years. Got cool again, got warm again, it's been getting a little bit cooler. You know what this cold period, which occupies most of this time, is called? That's the Ice Age. This pattern, by the way, repeats back at least about 1 million years. We have data from ice cores that show this sort of consistent repeating of warm, followed by cool, followed by warm. Going right along with this and fitting almost perfectly is the carbon dioxide concentration in the atmosphere, which was at the lowest point in the Ice Age, a little below 200 parts per million. That means if you took 1 million milk jugs and gallon milk jugs and filled them with air, 200 of them would have carbon dioxide in them, or you separated them. Before the start of the industrial era, it was about 280 parts per million in this warm period we're in now, that civilization evolved in. There's where we are today. Now that's not a cartoon, that's a real graph of real data plotted on this time scale. This spike is bigger at this point than the variation, or about the same as the variation that makes the difference between an ice age and not an ice age. Now, I like to get people to think about that, because what was it like at that point right here in Vermont? What was it like if you were sitting in Vermont? There would be ice. How much ice? About 2 miles of ice on top of Vermont. So the difference between this level of carbon dioxide, where we were before we started dumping it in the atmosphere, and this level in the ice age, is 2 miles of ice on Vermont. That's also, by the way, the difference between a temperature of about 6 degrees below this average versus a degree or so above it. So consistent with a global temperature variation of about 6 degrees, or a carbon dioxide variation of roughly what we've added, going the other way is the difference between 2 miles of ice on Vermont and nice spring weather, where we can observe the phenology. Is anyone involved in a protest organization started by Bill McKibben? Yes. What's the number? 350. I keep arguing with Bill that he needs to be more quantitative, so I was delighted when he took on that number. But I suspect if you ask many of his followers why, they might not be able to tell you, but they could if they'd read this paper by Jim Hansen. Here's Jim Hansen, climatologist from NASA. Here's Bill. Target atmospheric CO2, where should humanity aim? And I've adapted this graph, but here's the main point they make. If you go back in the record 60 million years, you find there was a time about 35 million years ago when global CO2 dropped below 450 parts per million. Back there, it was above 450 parts per million, and the world was ice-free. At about that time, the Antarctic ice sheet began forming and continued to the present. These colors represent when it was more intense and less intense. This is millions of years, remember. And the northern hemisphere ice sheets formed much later, about 10 million years ago, as the carbon dioxide continued to drop. But the point is, it's pretty clear that if the carbon dioxide got above 450 parts per million, and there's absolutely no way it's not going to get that high in the next few decades, no matter what we try to do, probably, the world will be ice-free. Now, it will take thousands of years, but there's about 200 feet of sea level rise in the ice that's in the Antarctic and Greenland particularly, and we'd have a problem. So that's a look at why that number 350 is there. They sort of looked at 450 and said, we certainly can't go near 450. What's a good number? 350. Unfortunately, we're closer to 450 today than we are to 350. So I've come to my last big question in my last few minutes. So what is the future? First of all, the future comes from big computer climate models. And people say, well, garbage in, garbage out. They don't really tell us anything. Why do we believe these models? There's a number of reasons. First of all, here's a wonderful experiment nature gave us. We can't experiment with the climate. Well, we're inadvertently experimenting with it. But here was the eruption of Mount Pinatubo in 1991. Remember I showed you the graph of the warmest years? And the early 90s weren't on there, although 1990 was. And the reason is because this volcano erupted, put dust into the global atmosphere, and actually dropped the temperatures by about half a degree or so. And then they gradually recovered over a few years. So the early 90s were a cold time on Earth because of the eruption of Mount Pinatubo. And Jim Hansen, the same one who wrote that paper, he and some colleagues got together and said, let's model at the time of the eruption, based on our best estimates of how much dust went in the atmosphere, what the global temperature is going to do. And they made some models, different assumptions about the dust. That's what these dashed lines are. And they reproduced quite nicely what the global temperature actually did using these global climate models that were available in the early 1990s. They're a lot better today. Here's an experiment in which global climate models were initialized with the climatic conditions of about 1880, and they were allowed to run forward in time in several conditions. So what we have here are a black graph, which is the actual observed temperature. We have the pink, which is the models run with the inclusion of the greenhouse gases that we human beings have put in the atmosphere, and those sulfate aerosols that tend to cool things, so they're in there too. That's what the pink is. The curves, are, the dark lines are sort of an average, and the pink is a range that different models gave us. And the blue is the same thing, but without the anthropogenic effects. So the anthropogenic effects explain very nicely. The models track exactly what seems to be happening, whereas the ones where you leave out the anthropogenic effects don't seem to do that. A much harder thing to predict is precipitation. It's much harder to predict than temperature. And here are some observed and predicted by models 20th century precipitation patterns globally by area in the globe, by computer models and by what's observed. And again, these models were started in the 1880s and run into the 20th century. And they look pretty similar. There's this thing like a swan or something flying along here with a lot of precipitation at the equator extending upward. It's not bad. Not perfect, but it's not bad. So we believe these climate models. So what's our climate future? What can we expect? What will be the impacts? And what can we do to mitigate climate change? Well, this is not science anymore, because the answers to these questions depend on the choices we make. And in the IPCC, if you've studied any of the earlier IPCC reports, everything is different now. We're talking about these things called RCPs, representative concentration pathways, and what they give is a number, 8.5, 2.6, 4.56, whatever, that is the best estimate of how much we will have upset the balance, or that energy balance of Earth, by the year 2100. 8.5, the business as usual scenario, suggests we will have been having an additional, or 8.5 watts coming on every square meter. So I take a 10-watt light bulb, roughly, and I shine it down on a square yard, roughly, and that's what's going to be the added energy then, globally, all over the whole planet. 2.6, we only get to 2.6 watts on every square meter. We're now at about 2.8 is the amount of imbalance we humans have done. And so these are just some looks at what the CO2 concentrations would be. The 8.5, the business as usual, gets us up to about 1,200 parts per million. The others get us well over twice the pre-industrial, which was 280, so this is 560. So most of the scenarios get above that, except for this 2.6. And the 2.6 scenario is the only one that really gives us a chance of limiting the industrial era temperature rise to 2 degrees Celsius, which is what the world has agreed on, except now it's agreed on maybe 1.5 would be better. 2.6 requires us not only to stop emitting CO2 to the atmosphere, but actually take some out. What are the projected temperature increases? Well, you run a whole lot of different models under these different scenarios, and the projected temperature increase from 1850, so from pre-industrial, range from just a little bit. This is in 2000. The zero is at 2000. That 2 degrees or 1.5 is from here. So we're already up about half, and we go up at about 1. So the best we can do is probably about 1 degree with these RCP 2.6 that requires removing carbon. If we go to 8.5, we're going to go up about 4 to maybe even 6 degrees Celsius from 2000, another degree or half a degree or so, a degree from the pre-industrial times. And here's what it looks like globally relative in the last 2 decades of this century relative to the last couple decades approximately of the 20th century. These are scales that show how much increase there will be with the business as usual. It's pretty dim, pretty bleak. And I'd like you to notice one other thing. Look at this one a minute. Focus on this map. The colors represent the increases in temperature. Where do you see the biggest increase? In the Arctic. A little bit in the Arctic. Okay, second. Where's the second place you see a big increase? Take a look. Where? Landmass. On all the landmass. North America, South America, Africa, Asia, Australia. So remember that when someone says, oh, the temperature's only going to go up by 1.5 degrees, we're going to hold it to that. On the land areas, it's going to roughly go up twice as much. And in the Arctic, a lot more than that. So it's not an even distribution. Let me end with just a few more comments. Why does it matter that the temperature goes up a few degrees? First of all, as I just said, that's a global average. Many areas will warm more. And in particular, virtually all land will warm more than the global average. As I showed you before when we talked about the ice ages, the difference between the present warm period we're in, you know what it's called? It's the Holocene, except maybe we've now transitioned to the Anthropocene. And the ice age time is about 6 degrees Celsius, about 9 degrees Fahrenheit. So even if the temperature goes up, if we raise the temperature by 3 degrees from pre-industrial, that's not that much, but it's half that much. And so that's hugely climatologically significant because that's the difference between nice spring weather and 2 miles of ice on top of us here in Vermont. So even a few degrees is climatologically significant when it's a global average for the whole planet. And finally, this one is a little more subtle. If the mean temperature goes up a little bit, you don't notice that today, May 11th, is a lot warmer than May 11th was 20 years ago. It might be. It might even not be. It might have been 80 20 years ago. You don't notice those small variations. And what that means is if you sort of look at the probability of getting a certain temperature, so I start with the red curve, and well, there's a probability that it will be 15 degrees Celsius, and a little less probability it'll be 10, more there'll be 20, less it'll be 20, and so on. It gets this bell-shaped curve. If the temperature goes up globally, we change that curve a little bit. We shift it to higher temperatures. Temperatures around the mean, which is most of them, you don't notice that much. I mean, 2 days ago we had a frost. It was 29 degrees at my house. Whoa. This morning it was 49 or something. We don't know, those variations are much bigger than the little variations associated with global warming. But look out here at the extreme, and let's blow that up a little bit. So out at the extremes, if you look at those two curves, the red one comes down much faster than the blue one. And what that means is there's a much higher probability of extreme high temperatures and a much lower probability of extreme low temperatures than just a few degrees change in the mean temperature would suggest. If you blow that up even further, you see that difference magnified. So although there are very few days when the temperature is this high, there are, relatively speaking, many, many more of them under the scenario where the mean temperature just shifts a degree or so. So a few degrees matter, and any of your skeptical friends say, oh, we're only talking a few degrees. Here's 3 reasons why that doesn't matter. You know, someday I'm going to stop talking about skeptics, because everybody's going to be convinced. But when one of the 2 major presidential candidates has a different theory, I've got to keep talking about skeptics, because we've got to keep arguing against them. Sea level is going to rise somewhere between a quarter and a full meter over this century. There's a new paper by Jim Hansen came out in February that suggests it's going to come even sooner, perhaps. Here's sea level. Sea level doesn't rise equally around the globe. That sounds a little odd, but it doesn't. We won't go into that. Ice and snow coverage is going to decrease under these different scenarios, less under the RCP 2.6, more under the business as usual. Here are some glimpses of what the Arctic ice pack will look like in the last 2 decades of the century. No ice left under the business as usual scenario. Something I haven't mentioned, the carbon dioxide we're putting in the atmosphere, in addition to changing the climate, dissolves in the ocean, makes the oceans more acid. That makes it harder for shell-forming organisms to form their shells and changes the whole ecology of the oceans. And the oceans are getting more acidic, and they're going to continue to get more acidic, and they get dramatically more acidic under the business-as-usual scenario. So what are the best guesses for what's going to happen? Most climatologists would tell you we're going to see a temperature increase of about 3 degrees Celsius this century. That is way above what the nations of the world have decided is safe. So we're going to have to work really hard to prevent that. We're going to see sea level rise of probably half a meter and maybe more. We're going to see ice and snow going down. We're going to see ocean acidification. 3 degrees is a lot of climatologists' sort of best guess for where things are going to be. And let me end with this last slide, which reminds you that it doesn't stop at 2100. Most of the scenarios we talk about run to 2100. But if you look at what's going to happen in the future, and we assume we manage to peak our CO2 emissions somewhere in the next century, maybe mid-century, nevertheless, it's going to take another 100 to 300 years for the CO2 concentration to stabilize, and it will be higher than it was in the pre-industrial times. The temperature takes a few centuries to stabilize. The sea level is rising for 2 reasons. One is the expansion of the water as it heats, like the fluid in a thermometer expands. That's going to take centuries to thousands of years. And the melting of sea ice, that takes a lot longer. That may take thousands and thousands of years. So we've set into motion changes in the Earth's climate system that are, in timescales we humans like to deal with, essentially unstoppable. So we've got a lot of work to do if we're going to make things a little bit less bad than this picture presents. And I'll stop there and take any questions. Thank you.
On a percentage basis, what is the contribution to expansion?
Contribution in the back there. Question in the back first.
I was just wondering if you could address sunspot activity and
Yeah.
how that affects weather and
That's a good question. I've actually had students do work on that. If you look at the sunspot cycle is a cycle that occurs on the sun for magnetic reasons. It goes on every 11 years. There are more sunspots and then fewer. And there are changes in the sun's power output associated with that. And you can just barely see in the climate record the variation associated with that in the average temperature. It's a few hundredths of a degree. It's nothing compared to what we've seen here. I actually had a couple of interesting student papers on this where they looked at a map of the United States and they studied weather stations. They averaged all the weather stations for a state. And it's interesting. You can see the states in the Midwest, that variation is bigger because they're away from the water that tends to moderate temperature changes. But that's negligible. What's more important is the question of whether over longer times, decades to centuries, has the sun's overall power output changed. And it has. And that was included in those natural effects that I showed you, but they are still small, tiny, 10% or less of what the humankind is doing. So it's a very good question. The sun is not the answer, although some skeptics will tell you it is. Now, you had a question.
The rising
Yeah.
of sea levels. What's the contribution?
Good question. It is very roughly 50-50. It varies, and I think the balance is swinging toward the ice melting. The ice that's floating, which is the Arctic ice, does not contribute to sea level rise. Put an ice cube in a glass of water, let it melt the water, it doesn't overflow. So it's only the Greenland, it's mostly the Greenland ice pack that's contributing now. But it's roughly 50-50. They're both significant.
And is acidification a variable factor significant in that and how much expansion takes place?
No. No, it doesn't affect the water's physical qualities much. Another question back here. Wait, we need some more people, but yeah.
I'm reading a book right now called the year of 1960, the summer of 1816, about a volcanic explosion. I'm just wondering.
Tambora, is that the one?
Yes.
Yeah.
And how it affected the Earth for several years.
Yeah.
And I'm just wondering, whenever there's a volcanic explosion like that and the whole Earth is basically, the atmosphere is affected, is that always finite?
It's finite in time.
Yeah.
And, there have been some serious times when the planet was significantly cooler, partly due to very big volcanic eruptions, partly due to changes in the sun that we don't fully understand that occurred in what was the so-called Little Ice Age in the 16 to 1700s. But Tambora was it was bigger than Pinatubo. And, half a degree for a couple of years can affect agriculture and things. So but the problem with volcanoes is they're sporadic. They're not a steady thing like greenhouse gases emitted at this rate, so it's a little hard to incorporate them in the models. But they definitely cool things.
You talked about we probably ought to be removing CO2.
Yeah.
How do we remove?
Well, easy way is to plant a lot more trees. There are other ways. There are certain rocks that when they weather, you're exposed to air, they take up carbon and make carbonate minerals. I don't know the chemistry because I'm not a chemist, but people have talked about grinding up. I think Madagascar has a lot of this, and you grind up and put vast fields at the top. People have talked about the building of these ships that have not exactly artificial trees, but have these structures that absorb carbon dioxide. One of the most clever ways, though, that's now getting a lot of attention is to burn biomass. That is, burn wood, burn stuff that was recently grown material. That stuff takes carbon out of the atmosphere, so when you burn it, it puts carbon back in the atmosphere, but in principle, although not necessarily in practice, that's carbon neutral because you took the carbon out, you put it back in, like Middlebury's biomass plant that it claims is carbon neutral. You burn the stuff, carbon goes up, but you take it out. But if you then do this thing called carbon capture and storage that people have talked about for some years with coal plants, they want to actually capture the carbon dioxide coming out and pump it underground. If you do that with a coal plant, which is very expensive and difficult, you can make the coal plant not be putting carbon in the atmosphere. But if you do it with a biomass plant, you've actually taken carbon that the plants took out of the atmosphere and sequestered it underground. And so that's called biomass with carbon, BCSS, I think. And that would be a clever way of removing carbon from the atmosphere with the help of plants and still getting some energy out. So that's another way of doing it. And there are other schemes, but it's a huge volume. A single large power plant, coal-burning power plant, puts 1,000 tons of carbon dioxide in the atmosphere every hour. There's a lot of, if you're going to react that with some other chemicals, if you're going to pump it underground, it takes 40% of the energy that the power plant produces, which is one reason we're not doing it. So it's a very good question, but we're going to have to figure out some ways.
What effect might the decrease in population have?
What decrease in population?
That's exactly what I mean.
Okay.
I mean, would population control help us?
I'm a big advocate of the world has too many people, and I'm still hoping we're going to see 9 billion peak around 2050. but the most latest studies by the UN suggest we're going to continue growing. The problem is the population is not occurring in the developed world. It's occurring in the developing world, which has every right to our standard of living, and our standard of living is based on energy use. So there's a justice issue there. The other issue is, some of those parts of the world are in fact developing rapidly. China in 2010 became the largest producer of CO2. And China has had a population control measure. You can argue whether it was a good one or not, or whether it was draconian. But so I think yes, we have to stop population growth. That's important for lots of reasons, but it's not going to help this problem immediately, because the people who are producing the most CO2 already have stable populations, and the people who aren't producing much CO2 are going to be producing it whether or not their populations grow. Doesn't mean we shouldn't have population control, but I don't think it's as big a factor in this as you might think for those reasons.
In the circle graph, I noticed nitrous oxide. What's the significance of that section of that?
Nitrous oxide is one of the things that comes from the breakdown of agricultural fertilizers. So that's mostly agriculture. I forget what the other sources are.
It was a different section than agriculture.
Yeah, I don't know what the other sources are. No, that was in the gases.
Yeah.
That was in the gases section. That was different from the section by the sector producing it. So that was mostly from agriculture, from the breakdown of fertilizers that had nitrogen. Fran.
When we were in Ecuador recently, we learned a lot more about the importance of the forest there. We were in something called the cloud forest, but it's like a little higher than the rainforest. And they're having a lot of pressure to use the land not to keep it in forest, but to put it in agriculture and to grow beef.
Right.
So one thing that we could do worldwide is support
Yep.
the keeping the rainforest and the cloud forest
Yep.
intact
Yep.
rather than going to some of these
Yep.
fast food places
Yep.
that put the pressure on the land. So that's one of the things we saw right up front. We saw people actually burning the forest, these old, incredibly diverse forests, to put a few animals on there so they could have cash money in their hands.
Yep.
And that's something that I think, you think, well, save the rainforest. It's our lungs
Yeah.
that they're burning, and they're burning it because they need the money to pay.
Yeah. I mean, if we were all vegetarians, that would help a lot, because the total amount of energy that's used to make animal food is a lot more than to make plant food. There is another side to that, which is a little ironic, though. When we cut down tropical forests and grow crops, the crops are much lighter and more reflective. And so they actually have a temporary cooling effect because they reflect more sunlight. But that's countered by especially with slash and burn agriculture, by the putting the carbon dioxide into the atmosphere from that. Best thing you could do with that wood, if you are going to cut it down, is make it into furniture. Good furniture. It's going to last a long time, because then you've sequestered the carbon. Question there.
So I watched Bill Nye program. He was talking about climate change, and he talked with scientists and a different scientist, and that other scientists said that you didn't think there'd be a human being on the planet by 2030. Is there, even if humans actually try to do that, is there any way that would be possible?
That's a very good question. I mean, my personal take, I'm not quite as much an alarmist. I mean, I see those pictures, somebody says that, and they show the Earth kind of dripping and melting. It would be very difficult for us to make the Earth actually uninhabitable. We can make it a very unpleasant place. We're going to exacerbate the gap between the rich and poor countries. We're going to do all kinds of bad things. We're going to make a lot of things go extinct. But to make it totally uninhabitable, I think is probably not possible. There are those who argue we could do what happened to Venus, where an early greenhouse effect made Venus lose its oceans. But that Venus is closer to the sun, and that's probably why. So that's a very good question. And I actually am a little impatient with my fellow climate activists who sort of push too extreme a view. I mean, there are worse things that could happen to the planet. A nuclear war would be worse. Getting hit by an asteroid would be worse than climate change. I think we can manage climate change. How well we manage it is going to impact the quality of life, but I don't think the scenario you talked about is likely. That's my personal take.
Thank you very much for your talk. I really appreciate it. I have a question or comment that is not so much about science or policy, but more about PR.
Okay.
You repeatedly, as many engaged in this debate, do use the word skeptic. And I would submit that at this point, that's far too generous a term. I mean,
You're right.
Amy and I raised our children
Denier.
to be skeptical.
Denier.
I think
Denier.
skepticism is
Yeah,
good.
yeah,
And I
yeah,
think
you're
there's
right.
a difference between ignorance or willful ignorance and
Yeah,
skepticism.
good point. And I believe Michael Shermer, who edits the magazine The Skeptic, made exactly that point in a column in Scientific American recently. Yep. And as the years go by, these people it's clearer and clearer that these people have their heads in the sand. So, a good point. I will avoid using skeptic. I'm going to use the word denier. Is denier okay? Yeah. Okay, yeah?
I have two things I'd like you to discuss a little bit. One is the fire in Alberta and what it's doing and what it's likely to do and if it's going to affect the oil and gas fields.
Speak louder.
Oh, sorry. The fire in Alberta.
Yes.
The second thing is two people have talked to me lately. One about biochar on your own land. And I think that's what you were talking about with industry. And the other is sequestering carbon in agriculture through how you do it.
Yes.
Diversity and all kinds of things. Could you talk about
So those are good questions. I don't know a lot about the fire in Alberta. And, as I gave you some news items that said maybe global warming has had a role to play. If global warming has had a role to play, it's in producing in Alberta a time of very high temperatures, higher than normal temperatures, longer such time, and more drought, because climate change exacerbates both drought and deluges. So if climate change had a role in that particular fire, and people will work the statistics, and somebody's going to say it 50% likely global warming made this fire worse, but it didn't cause it. The irony for me, and I've implied in your question too, is that the fire, of course, is threatening the fields that make the fossil fuels that make the global warming, and that way of making fossil fuels is particularly bad in terms of CO2 emissions. But you can't say global warming caused this fire, but it may have contributed. The second question is interesting. I mean, there are many ways to do agriculture better, and one of the goals is to avoid the loss of carbon to the atmosphere. And I'm not an agronomist, I don't know the details, but when Middlebury College says it's built this beautiful biomass plant, we're now carbon neutral. Well, if you look at the processes of harvesting timber in the forests, they result in soil carbon escaping to the atmosphere, and for that reason, Middlebury College really shouldn't make that claim. And it takes decades, maybe 80 years, about the lifetime of a coal-fired power plant, for a wood-fired system to become truly carbon neutral. But anything we can do to keep carbon in the ground, and this idea of biochar, and I don't know a whole lot about it, but so I think you make sort of a charcoaly stuff and you incorporate it into the soil, and it helps the plants grow, and it puts carbon there that might have otherwise been in the atmosphere. Those are all good things. And the world is a big place, so agriculture and forestry also have a big role to play in mitigating climate change.
Thank you.
Susan.
I keep coming to this question of keeping the fossil fuels in the ground.
Yeah.
Which is hugely important, and a lot of people are doing various things to try to do that. And then I come up against this really discouraging apparent phenomenon where, on one hand, you're keeping it in the ground, and on the other hand, commerce is just finding another way to use it and put it in the air. The most recent disturbing example to me is Mars exploration. People going to live on Mars or whatever. The space, the whole idea that you have to use fossil fuels, at least presently, to get to space. And how can we inject some hope into that scenario? It just seems like it's all going to get used sooner or later or something.
Well, I get a little quantitative there. I'm not worried about attempts to go. I think it's stupid to try to send people to Mars, but for other reasons. If you were to calculate, and we don't burn fossil fuel, we burn hydrogen, although we have to make it with fossil fuels or nuclear or something. But if you were to calculate the carbon footprint of the Mars program, it's negligible compared to a city's worth of cars. So I would really focus on the city's worth of cars instead. I don't know that I agree that we keep finding new uses for fossil fuels.
Well, we just get bigger cars.
Yeah, we do get, as soon as the price went down, we got bigger cars. On the other hand, Peabody Coal went bankrupt. So I think the message on that is mixed. And to get local, the message on the pipeline is very mixed, because the biggest argument, in my mind, against the pipeline is that we are putting in place a fossil fuel infrastructure. The biggest argument for it is it will displace oil, which is a much worse fossil fuel because it makes much worse carbon. And these things are subtle. And I think the question of something like the Mars program, that doesn't bother me. What bothers me is the justice issue I raised. Everybody in sub-Saharan Africa and everybody in South Asia and East Asia wants a car or two. And if we're going to have them, they have every right. And that is a far huger impact than...
We as a species actually have the right to the current U.S. standard.
Well, I think if we have the right to it, then everybody else does. Maybe we don't have the right to it, but we're not doing much to give up what we treat as a right.
And that's what I'm saying.
Yeah.
Congress continues to promote the idea that the standard of living is adequate and should get better.
Yeah, I mean, we are making progress slowly on some of these things. I mean, the fleet mileage of cars is going up. With the recent drop in gas prices, we had a little going the wrong way there. But the coal is being supplanted. Coal in 2015, for the first time, the majority was not the biggest producer of electricity in this country. For decades, coal was the dominant, the single biggest chunk of our electric mix. And in 2015, that switched to natural gas. Now, you can argue both ways about natural gas, but our carbon emissions went way down because of that. So I think there is progress. I mean, it's not hopeless. We have to make the progress a lot faster, and it has to be a lot more substantial. And we certainly shouldn't be making up substantial new uses for the fossil fuels. I agree completely we should leave them in the ground. And I think there's no way we can burn all the coal, of which we have hundreds of years left, without damaging the planet very, very, very badly. I think,
I want to follow up on Annie's question. And I'm just wondering, has anyone modeled what would happen if the college biomass plant were to turn into a net biochar producer and extract the heat through pyrolysis and then quench and then move that off into biochar, and it would obviously use more. It would use more feedstock. But has anybody modeled?
I don't think so. I don't know for sure. I mean, that's a gasifying plant now.
Yeah.
And I believe what's left over is used for fertilizer, but I'm not sure. It may already be incorporated in the soil.
In order for it to become biochar, it would have to be quenched.
Yes.
At a certain point.
Yeah, and then you would not get as much energy out because you'd have the carbon that was. So I don't.
Wondered if anybody
I don't think so, and I don't. I doubt that the plant is set up to do that.
No.
Right. Yeah.
If there are no more questions, I think perhaps we can.
And thank you all for coming.
Thank you.